So in this video, I'm going to be doing a series of problems, and the theme of all three of these problems that I'll be doing is mixing and matching our energy analysis with other parts of the course that we've done. So the first is problem 15. So the picture is a little deceiving. For problem 15, you'll see this. So that's what that looks like. What they don't show very clearly, they have the bottom of the loop is a little bit higher than this point, but that doesn't really matter. This is more rightfully what this point should look like. And they call this point A. A certain height h is labeled here. We have this bead that's allowed to go on this track. You can think of it kind of like a ball rolling and going through a loop-to-loop, or a bead going on this track, as they say. And then this little loop-to-loop has a radius r. And we are asked the question, a bead slides without friction around the loop-to-loop. If the bead is released from a height of 3.5 r, what is its speed at point A, right? So h is equal to 3.5 r. And what I want to know here is, what is the speed at point A? So let's go through our process. It is frictionless, so this is a nice simple process from here. The first thing we're going to do is draw a picture. Voila, picture done. Second thing we're going to do is we're going to put where our potential energy is equal to 0. I'm just going to choose UG is equal to 0 here. It's nice and convenient to do it from that position because actually everything is already kind of measured from there. Next, we're going to label the points. It's kind of annoying that this is point A because I kind of want to think of these things in sequence. So I'm just going to call this point B. Normally I would call that A and that B, but the problem made some decisions for us that I think were inarticulate. The next thing that I like to do in these problems after doing that is think about, well, what's the total energy at each of these places? Well, the total energy at point B is just going to be potential energy to gravity, and the total energy at point A is going to be the potential energy to gravity at point A plus the kinetic energy at point A, right? So I have a nice, clear idea of what's going on at each of those points. So next, what are we doing? Well, next, what we're going to do is I want to link my points. I know it's a frictionless surface, so the law of conservation of mechanical energy is true here. So I can say that the total energy at point B is equal to the total energy at point A because the work done by non-conservative forces between those 2 points is equal to 0. Awesome. So then I can put in that UG at point B is equal to UG at point A plus KE at point A. And now I can substitute in what I know. I know the equation for UG is just mgy, and y is measured, remember, from our UG is equal to 0 line. Any position above that line has a positive y value. Any position below that y has a negative value. I made the bottom, the lowest point, the 0 level, so I don't have to worry about negative y's in this. So what do I have here? I've got mg, and then we know this is 3.5 r. Is equal to mg, and then what's the height of A? Well, that's 2 radii above the ground, plus 1/2 mv at A squared. Oh, look at this, nice and simple. I've got an m in each of my terms, and so that can go away, and now I can move things around. So I can subtract over this, and I get g times 1.5 r is equal to 1/2 VA, multiply the 1/2, 3GR, square root of both sides, plus or minus, because I've got a square root. We're looking for a speed, so there we go. I now have an expression for the speed at point A. Awesome. And then the B part of this just asks, what's the normal force here? So when the object is here, we know we have Fn acting down. We have gravity acting down as well. And so I can then do part B. Sigma FR is equal to MAR. Got to remember that it's going around in a circle, so we want to use our radial ideas. Both forces point inward, so Fg plus Fn is equal to mv at A squared over r, right? Because that's what happens there, that the radial acceleration, which is that's supposed to be, is v squared over r. And so mg plus Fn is equal to m and our v squared, radical 3gr squared over a capital R And we can see what happens then, that Fn is equal to, well, when all that squares out, the r and the square root squared is going to cancel. So I'm going to get 3mg minus mg, or get that Fn is equal to 2mg at that location. So there we go. Now, an extension from this problem might be then, if that's true, whether h is 3.5 r, you might ask, well, what is the minimum height that this has to be such that this bead makes it around the circle? So stop the video for a minute, ask yourself that question, and we'll come back to it. So we are back. And so what we're going to do is the problem in reverse. But this time, what is the min speed at r, or at a point A? Well, we're going to use our force analysis in the same way we did in chapter 6 in order to say, well, I know that Fn plus Fg is equal to mv at a squared over r. And we're going to take the limit as v approaches v min. Well, if v approaches v min, we know that that thing should lose contact. Now, here's the thing. Let's pretend it's a ball rolling around rather than a bead on a track. We'd be worried about that Fn going to 0. That's what should happen at that v min. So that means I've got 0 plus mg is equal to mva squared over r, and therefore va, that should be va min, is equal to the square root of gr. Now I can take that back and go EA is equal to, or EB is equal to EA, work non-conservative is equal to 0, and I can steal my work from before because I've got the same potential energy function, but now I've got mg times y min is going to equal mg times 2r plus 1/2 m, and then the VA there is going to be the square root of gr, quantity squared, and so that becomes mg y min equals 2 mgr plus half mgr, right? Because that's what's happening there. And then the mg's cancel, right? Not the 2. And we're left with that y min is actually 2.5 r. So that 3.5 r is well above what it needs to be to remain in contact and make that circle, right? So trying to bring back some of our circular motion ideas back into this. Great. The next problem that we're going to want to look at is try and bring back some projectile motion ideas into this. So that's going to be problem 23. We're told a cannonball is fired from a cannon with a muzzle speed of 1,000 meters per second, angle 37 degrees with the horizontal. A second cannonball is fired straight upwards. So I've got this and I've got this, right? So we're told that the initial speed of both of those is exactly the same. So we want to find the maximum height reached by each ball and the total mechanical energy at the maximum height for each ball. Let y equals 0 at the cannon. So they're actually telling you that the UG is equal to 0 level has got to be there. So there we go. So I know, let's call this point A, we'll call this point B, and this point C. I know that the speed at point A, no matter which direction I launch it, is going to be 1,000 meters per second. I know for my second, or my first cannonball, the launch angle is 37 degrees. So let's just find those maximum heights. We're also told that the cannonball is 20 kilograms, as if that is going to matter for some part of this problem. So let's find those maximum heights. So the first one's pretty easy because I know this maximum height is going to happen when the speed of the object goes to 0, right? So when I shoot it straight up, I know the V at B is 0. So EA is equal to EB because the work non-conservative is equal to 0. Super straightforward. It's just got kinetic energy at the beginning. So kinetic energy at point A is equal to potential energy to gravity point B. Now, notice here I didn't write out the potential energy statements, or the total energy statements over here on the graph. Some people don't like to do that. So another place we can do that is just as we're plugging in for EA and EB here. That's perfectly acceptable. You kind of develop your own idea of how you're going to think about these problems as you're going forward. Right, so let's plug in. 1/2 mv at A squared is equal to mgy at B, right? Great, so once again, the masses cancel. Now, except here, I'm not going to cancel the masses. Even though, I can do that and solve the problem, we'll notice that the B part of the problem asks for the total mechanical energy at the maximum height. So I actually want these energy numbers. If I cancel out the mass, I don't get those numbers. So here we go. 1/2 of the mass, that's the speed, excuse me. So 1/2 of 20 kilograms times 1,000 meters per second squared is equal to 20 kilograms times 9.8 newtons per kilogram times what y at B is. So I'm not going to cancel out the mass because I want the number. So what do I have there? It is some fairly large number. I think I just moved that. So 1,000 squared times 10, right? Because 20.5 gives us this 10 million joules number, which is fairly impressive. Not really, but there it is. Y of B, right? And so I can then divide that through by that. And I can find the fairly large 51,002 and then there's decimals, but meters, right? 51 kilometers up into the sky. That is really significant. But then again, we're firing this thing at Mach 3 upwards, which is absurd. So whatever. Now, point C is interesting because I knew the speed went to 0 at point B, but the speed here is not going to be 0. So how are we going to resolve this? Well, remember I said the theme for these problems is using our previous physics knowledge here. What I will know is at point C, that the speed at point C is just the horizontal component, right? We know that VCY would equal 0. So VCX at that point, I seem to have lost my my pad here, my information. Let's see if I can get that back. Okay, just rejoining the Zoom with my other computer. Pardon me about that. And there we're back. Great. So I know that the x component here is all that's left, so VCX. And the great thing that I know here is that the x, we'll double up there, the x component for projectile motion is a constant. So that means the x component of the velocity at A is equal to the x component of the velocity at C. So all I need to do this problem now is find out what the x component at part A is. So VAX, very kind of appropriate for this day and age, is VA cosine of the launch angle. So 1,000 meters per second, cosine of 37 degrees. Plug that into our calculator, and that is going to be 798.6 meters per second. So that now I can do that EA is equal to EC because the work done by non-conservative forces is equal to 0. Now I'm not going to plug in anything over here because I know the energy at A is just 10 million joules. Done. The energy at C would be the potential energy at position C plus the kinetic energy at position C. So now I can plug in for these. So 10,000 joules mgy at C plus 1/2 mv at C squared. And then we can finish this off. So 10,000 or 10 million, joules is equal to 20 kilograms times 9.8 newtons per kilogram times y at C, which is what I'm looking for, plus 1/2 times 20 kilograms times VC, which we know to be 798.6 meters per second, whatever that component is at that place. So now let's just do some calculations. I got some big numbers here, so I'm just going to jot them down so I don't mess them up. Right, that's good enough. 196 YC, and then 10 million. Okay, I just have a fairly simple calculator here, so I don't want to try and do too many steps at the same time. That's just something that I've done as a practice. Okay, and then divide by 96. Okay, and we get that YC is 18 kilometers instead up in the air, which makes sense that it is less. So there you go. And by the way, we've already done part B because that's right here. It asks for the total mechanical energy at positions B and C because the work done by non-conservative forces is 0. It doesn't matter what direction I fired in, that's going to have the same total mechanical energy because there's no reason for the total mechanical energy to have changed. Remember, the work done by non-conservative forces is the change in total mechanical energy. If no non-conservative force does work, then the energy, total energy in the system doesn't change. Remember, not non-conservative forces acting, but doing work. Now, there is a non-conservative force in this problem. It is the launch of this, but we are looking at this thing once it's been launched. All right, one final problem I want you to, that we're going to do here is problem 16, right? So problem 16 says, I've got a mass attached to the bottom of an uncompressed spring. And they should say that spring is, well, they say it's hung vertically, right? So there's that spring, and there's that mass. And it's held there at rest, and then it's dropped. So what's going to happen to that spring? Well, that spring is going to drop down to some position down here where eventually it will come to rest again, right? Because that's the place where it's going to stop. But it also asks, that's actually the B part. It also asks where the maximum speed is. And that's going to be somewhere in the middle. So I'm going to draw this spring or this mass at 3 different positions. And we're going to call these positions A, B, and C, right? So we know that initially we have the force of gravity acting downwards, it's going to accelerate downwards. But the second this spring starts stretching, there's a force upwards. But that force is really small to begin with, because remember, the spring force here is negative K. Now, we would normally say X, right? But let's just say negative KY, depending on how we do some declarations here. But we have to declare Y is equal to 0 for the spring force to be here. Because by definition, we said in the spring force that this position had to be with respect to the natural length of the spring. So that's a fairly big constraint on this, right? So this is going to have some interesting implications. We know that this thing is going to speed up, as I said, because the gravity force is bigger than the spring force initially. At some point here, they're going to equal, and then the spring force is going to be bigger than the gravity force, and it's going to slow down. So this position here where it achieves its maximum speed is going to be the place where it stops speeding up and starts slowing down, i.e. where its acceleration is equal to 0, right? But let's set up the energy problem, which is draw the picture, done. And next we're going to do is put our potential energies equal to 0 places. So this is going to be where my US is equal to 0. It has to be. By definition, in the spring potential energy, 1/2 kx squared, which in this case we can say 1/2 ky squared, that position has to be with respect to the natural length. We also have to do a gravitational potential energy. Now, here's the thing. You can literally choose anywhere, but I'm actually going to choose UG is equal to 0 to be this same line for simplicity's sake. Now, that's going to have an implication, which is that all of my y positions then are going to be negative, right? Because in this equation, UG is equal to MGY. Everything below the UG is equal to 0 line has to have a negative y value. Everything above has to have a positive. And that's actually going to make our problem solving a little bit easier. Because if we think about total energy statements then, the total energy at point A is going to be 0. It doesn't have gravitational potential energy. It doesn't have kinetic energy. It doesn't have spring potential energy. The energy at point B, it's going to have both spring potential energy at point C, actually, at point C, and it's going to have gravitational potential energy at point C, right? And then our B point here, it's going to have kinetic energy, gravitational potential energy, and spring potential energy. So there we go. So we want to know what is its maximum speed and how far does it drop before coming to rest momentarily. Well, let's just set up the energy problem first and we'll see what it says to us. So it says to us, Well, I know that the energy of point A is going to be equal to the energy of point B because there's no non-conservative forces doing any work here. I've got the spring force and the gravity force, both conservative. So 0 is equal to the kinetic energy at point B plus 1/2, mgy plus 1/2. And you know what? Actually, let's leave the spring force in terms of k, in terms of x, just so that we can see a distinction between those things. So we'll just call it negative kx, okay? Right, so this is going to be 1/2 kx squared, and we're going to see a link between those. So that's what we've got. Oh, I probably should have, I'm sorry, I should have put in the UG terms here, so I'm a step ahead of myself. So 1/2 mv squared plus mgy plus 1/2 kx squared. So let's just talk about those terms just to begin with. I'm looking for this. I don't know what my, I know what my m is in this problem. We're actually told the mass is 0.12. I know what my k is. I know what g is. Great. So I just have vb and the y and the k, the y and the x. Well, the way that we have this here, though, it's set up pretty nicely that our x value here, right, at any given position, so x, is going to just be the same thing as a negative y, right? Or if we want to here, I can say positive x is downwards, and therefore x is just equal to y in all of this, which is pretty nifty, right? Nice and simple. Now, what is that position? Well, here we go. That means we have to use our other knowledge, which is the force problem. So I can, when it's at position B, do the force problem. I've got forces up, and I've got a spring force up and gravity force down. So I'm going to do sigma Fy is equal to MAY in this case. And I know down is positive, so it's Fg. But remember, the spring force has the internalized negative sign, so I'm going to do plus Fs is equal to MAY. Now, the whole issue here is I'm looking for the place where V is maximized. So I know that dv dt is equal to 0 there because the velocity is maximized when its first derivative is equal to 0. That's the same thing as saying the acceleration in that dimension is equal to 0. So that means mg minus kx is equal to 0. Therefore, the position when that maximum speed is happening is mg over k, which is nice because I can calculate that. I have all those values. So 0.12 kilograms times 9.8 newtons per kilogram all over, and the k value there is 40 newtons per meter. And so I could put all that into my calculator, and you get 0.0294 meters. Whoops, there we go. So that's great because now I can come back over here and just plug in a bunch of values because I know 0 is equal to 1/2. My mass doesn't cancel because that doesn't have a mass term. 1/2 the mass, which is 0.12 kilograms, VB, which is what I'm looking for, plus 0.12 kilograms times 9.8 newtons per kilogram times that value that we found. But remember, this has got to be, in this case, a negative value, right? Because I'm below the UG is equal to 0 line. So 0.0294 meters plus 1/2 40 newtons per meter times, and here's the thing, it doesn't matter about whether this is positive or negative. Here, the way I declared the x here, I could put in a positive if I wanted to. It just literally doesn't matter, okay? So just a note on that, because I know that's going to confuse some people. These two things were derived very differently. This was derived because we said negative mg j hat. That means when talking about gravitational potential energies, up has to be positive. This thing was derived just along the x-axis, right? But here I can tilt that x-axis in any way I want because it doesn't really matter for the sake of the spring, right? Gravity x down, down is down is down is down is down is down. There's no difference there, right? But with the spring force, yeah, I can play with that a little bit. So anyway, I've got this plugin here. Let's put in some numbers and figure out what we've got. So I've got 0 is equal to 0.06 VV squared. The next term is going to become a negative there. So it's 0.12 times 9.8 times 0.0294. Okay, and this is going to be 0.03457444, whatever. Plus, I've got that same 0.0294 squared times 20 is equal to 0.0172. Like I said, I just have a crappy calculator on hand here. So right, and then divide over, and then take the square root of my answer, and I find that that maximum speed is 0.54 meters per second, right? Plus or minus, because I did take the square root. I'm looking for a speed, reject the minus sign. Whoops, that was off the camera. Okay, great. So that's that. We're also looking for the place of the maximum extension then, and I can do a similar process then, except now what I'm going to be doing is linking what's going on at position A and C. So the energy at A is going to equal the energy at C. Work non-conservative is equal to 0. 0 is equal to the potential energy of the spring at point C plus the potential energy of gravity at point C, or 0 is equal to 1/2 kx squared plus mg at y there. And now is when I really need to use my links between x and y in order to solve this problem, right? So when we did this before, x, so I think my x equals y thing, x is equal to negative y. I was right with that, right? Because if I have a negative positive y value, if I have a negative y value below this, because of this declaration, I'm going to have a positive x value, right? So that's what gets at us, right? So here I can put in then 1/2 kx squared plus mg, and I'll just do that substitution for negative x there. And now I have a nice quadratic. So 1/2 x, 1/2 kx minus mg. So that means x is equal to 0, or x is equal to, solving that, that's 2mg over k. That's a familiar looking expression. So if I go back here, oh yeah, look, the position where was that equal, like in that middle position, was mg over k. Oh, super interesting. This is just double that. So that must be double the original value we found, or 0.0588 meters, which is double 0.0294. Now, hopefully that makes sense to you, that this position here is just halfway between these two positions, right? And that should make sense from an oscillatory perspective. It is oscillating about this point. Now, oddly enough, what is this point that it's oscillating about? If we were to graph this, we would find out that this point here would be a stable equilibrium point. How do I know it's an equilibrium point? Number one, that's where the force is equal to 0. That's the definition of an equilibrium point. If I were to, let's say, have the mass here, at like start it there, right, and push the mass upwards, we know that the gravity force would be bigger than the spring force there, and a restoring force would perturb it back down and it would move down. If I pull it down, then the spring force is bigger and it would move up. So here, interestingly enough, the restoring force is actually a combination of the gravity force and the spring force. It's not just one or the other, right? There's something weird going on there. Now we'll explore that weirdness in chapter 13 when we look at this system as something called the simple harmonic oscillator problem. But just so you know, we can do these problems. We can bring in our ideas about circular motion. We can bring in our ideas about projectile motion. We can bring in our ideas about actually not simple harmonic motion, we haven't done that yet, but forces, right? To find that place of maximum speed, we can talk about forces. So there are some problems for you.